Very good morning, my dear student friends. We will be continuing the problem which was given yesterday. Well, there are 15 samples, and for each sample, the defectives have been given in the form of the table. We need to determine the trial control limits for the appropriate control chart and state whether the process is in control. And second one is, what will be the new value of the new fraction average if some obvious points outside the control limits are eliminated? That is what we need to find out. Now, if we look at that one, we can see that obviously the sample number 4 and 9, they will be falling outside the control. They appear to be on these samples. It appears that the number of defectives are abnormally high. But let us try to find out that one. Because here we have seen that the sample size, here it is given is 400, okay, and which is fixed for all the samples taken. So the sample size is 400, and the total number of defectives, if we add up all those things, it works out to be 66. That means the first sample 2, second 5, 0, fourth 14, like that. If we add up all these things, that is the number of defectives. Okay, defectives I is equal to 1 to 15. It works out to be 66. Hence, we can find out the P bar. The P bar is total number of defectives divided by total numbers inspected. The total number of defectives are 66. The number of lots are 15, and each lot size is 400. That means 400 into 15. So if you work out, it works out to be 0.011. 0.011. So yesterday itself I had told you that since the sample size is same, then we are going to use NP chart. However, whether we are going to use NP chart or P chart, we need to calculate the average fraction defective. That is the must. That is what, without bothering about it, I have calculated this thing. Okay. Now, we decided that the NP chart is to be used. If the NP chart is to be used, what are the upper control limits and lower control limits? That I can delineate over here. The upper control limit for NP chart is NP bar plus under root NP bar Q bar. Center line is NP bar. Lower control limit is NP bar minus under root NP bar Q bar. Now P bar we have found out to be 0.011. Okay. Hence the Q bar is 0.989. Q bar, this is 0.989. And average this thing, we have to find out the number of defectives, that is NP bar. NP bar, that is equal to 400 into 0.011. Okay. So that works out to be 4.4. Okay, center line is 4.4 average. That means The question comes now whether I should take average as, because there cannot be 4.4 number of defectives. It can be either 4 or it can be 5. But always I told you that whatever the first integer is there, that is to be taken. That is 4. We will consider that the average number of defectives are 4, not 5. Even if it were 4.6 or 4.8 or 4.9, then still we would have considered. We would not have approximated. Even if it were 4.9, we would have considered it to be 4. Similarly, for the upper control limits as well. So, if we calculate the upper control limit, that is NP bar plus NP bar into Q bar square root. That means if we calculate that upper control limit, I will write it down here. This is 4.4 plus and the square root. NP bar here is 4.4 into 9.989 square root. That is what I need to find out. If I find out like this, it works out to be 6.25. 4.4 into 0.985. Sorry, I made a mistake here. It is to be upper control limit is multiplied by 3 sigma limits. 3 sigma limits is forgotten here. It should be 3 sigma limits. Okay. So 4.4 into 0.989 approximately 4. That means approximately it is square root of 4. That is 2. 3 into 2. So it will be something around 6.25. So the upper control limit is going to be 10.65. Because number of defectives here 10.65. I can't find out that for 10.65 or 10.5. So what we will fix is, if it crosses 10, then the process is out of control. That is 10 we will be considering. Try to understand. Similarly, lower control limit 4.4 minus 6.25. So this is a negative value, so that I will consider it to be 0. That means the control limit, whatever we are going to establish, our lower control limit is 0, central line is 4.4 or 4 you can write, and the upper control limit is 10 instead of 10.65. But if you take the fraction p, then okay, we can express it in fractions. But here, really, when you are setting up, it will be like that. That is what yesterday I was telling, that the number of defective, it will be more effective, more appealing, not the fraction defective. Because we don't understand 0.011 average this thing, fraction defective. We don't understand something like that. But now we can understand 4 defectives. Yes, I can understand. 4.4 defectives, I don't understand. So if the control charts are established, what we will do is, we will see here. So there are 15 points, 1. So I am taking the time so that I am explaining it in full. Okay? Because it involves, compared to the previous problem, it involves some other aspects which I want to drive at. Okay? So this number of samples are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are number of samples. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So on this one I will mark it to a particular scale. Okay. Now approximately if I look at it, it is 10.65. Okay. The upper control limit, and the central line is 4.4. So almost that means If I take this one as 0, so almost double this one, that means I'll mark this one as the central line. As usual, the central line is a solid line. So let me say that it is 4. Instead of 4.4, I can mention it 4. Try to understand. Now, then this will be something 10. Instead of 10.65, I am mentioning it as 10. So I should have drawn this one as a dotted line. So this is upper control limit, NP chart, central line, lower control limit. This is equal to 0. Sample number 1, if we go on comparing the sample number 1, it says that the number of defectives are 2. So that means what I will do this one here. Okay, this is 5, 6, 7, 8, 9, 10. So that means for first sample, this is the point. For second sample, the number of defectives are 5. Number of defectives, 5. Third, it is 0. Fourth, it is 14. That means it will fall somewhere here, 14. Fifth, it is going to be 3, 6, 0, like that. So they will fall under these things. But the ninth point, it is 18. Ninth point is 18. Like that, I can go on connecting them. It will behave like this. So again, so this will give, that is what is happening. This is I'll try to draw it fully so that you can understand it in a better way. Fifth one is 0. Fifth one is 3. Sixth one is 0. Seventh one is 1. Eighth one is 0. Ninth one is 18. Tenth one is 8. 11th one is 6. 12th one is 0. 13th one is 3. 14th one is 0. And 15th one is 6. This is how it behaves. It gives some lots of pulsations if you look at it. Suddenly, now it is below center line, first point. Second point, it is slightly above. Third point, it comes to 0. And again, fourth point, it rises like that. Because there must be the assignable reason. Here you can see that assignable reason was corrected or something happened. Then it started decreasing. So it decreased. Again, it went up. Again, it came down like that. This is what is happening. In fact, it should have oscillated along this central line. That is what we had expected. But it is not doing like that. This one shows that since the 2 points have fallen outside, because one cursory this thing, they have fallen outside the control limits. So the process is not in control. That is what it says. Is it understood? This is the comment about the process is, it is not under control. Why? 2 points have fallen outside the control limits. So we are not analyzing further than that. If all the points had fallen within the control limits and then again it is behaving like this, then I would have commented something else. But here we can see that it is possible to bring it down to 0 or 1 or 2, these things, defectives. So we can see that some 5, 6 points, they say that 0 defectives. It is possible, perfectly possible. But because of certain reasons, it is going, that is what it tells. You identify that. Okay, is it understood? Now the second part, if I look at it, so this is the part A. Determine the trial control limits for NP chart and state whether the process is in control. These are called as the trial control limits because whatever the points are given, the sample numbers and defectives are given, based on that one I have drawn and I am not estimating still. So these are trial control limits. Hence, if the some points have fallen outside the control limits, those things to be eliminated. If all the points had fallen within the control limits, the same control limits I would have carried forward. Try to understand, that would have become the standard control limits. That is why the name trial control limits. Still we are trying to establish, this is the trial form, trying to establish the control limits. Now when we move towards establishing the control limits, standard control limits, next step is what? We need to eliminate the points which have fallen outside the control limits. How many points have fallen outside the control limits? Out of 15, 2. So what are those? The point number, the sample number 4 and sample number 9. Sample number 4, it has got 14 number of defectives and 9 has got 18 number of defectives. So totally now what has happened? Earlier there were 66 defectives. Now it has become 66 minus 32 because we are eliminating these two. So in that case, the total number of defectives, so shall I rub it off, this one? This one I'll keep it as it is, this side I'll rub it off. Now revised P bar we need to calculate. How we are going to calculate? Total number of defectives, they are not 66, they are going to be 66 minus 14 minus 18. And the number of the total number of the articles inspected are not 6,000, that is 15 into 400, it is no longer that one, it is going to be 400 into 12. 400 into 13 lots. So 66 minus 14 minus 18, so this works out to be 34. This works out to be 5200. Okay, 34 by 5200 is the revised fraction defective. So that works out to be how much we have to see. This works out to be 6.5 into 10 to the power minus 3. Or if I take it to 538 or 54 I can say, or this is equal to 0.00654. Try to see, earlier the fraction defective was 0.011. Now the fraction defective, average fraction defective has been reduced to 0.00654. Okay. Again, I need to, based on P bar is there, then based on again this one I need to find out what is the upper control limit and the lower control limit. Okay. Again, the control limits, they work out to be, if I substitute these values, NP bar works out to be how much? If I multiply this one, NP bar 2.616. What this one? 2.616. And 3 under root NPQ, for this change this one, it works out to be 4.826. 4.826. Okay. So now, if I consider NP bar is now average value is 2 defectives, not 3. Don't consider that. Okay. And upper control limit is 2.616 plus 4.826. So this works out to be something around 7 and odd, but we are going to consider that it is 7 defectives. So the upper control limit, instead of 10, now it becomes 7 defectives. And the lower control limit, it is NP bar minus this 3 sigma NPQ bar. That means it is going to be negative, hence it is going to be 0. So the revised trial control limits, I call now, earlier it was trial control limit. Now it is revised. It is revised trial control limit. The revised trial control limits are the upper control limit, in short I'll write, is 7, central line is 2, lower control limit is of NP chart, it is 0. Again, this one is to be compared. Mind it, already we have eliminated point sample number 4 and sample number 9. So all other values, they should be within 7 number of defectives. But again, if we observe, all the points are 7, below, less than or equal to 7, but except one sample, which is the 10th. The 10th sample number, the sample, it consists of 8 defectives. Hence, yet the process is not under control. That is what it says. Because one point has fallen out of control limit. I will say that even though only one point has fallen, instead of 7 point something, it is just 8. Why? The reason is, we expected, when we are setting up 3 sigma limit, we expected out of 1000 points, only 3 would have fallen outside the control limits. But then that means out of 15 or out of 13, how many should have been expected? 0. 0 points should have fallen outside the control limit. But here, 1 point has fallen outside the control limit. Hence, the process is to be stopped and investigation is to be made. This is the answer. That means still the process is not under control. Okay, we want to, because he has not asked next what is to be done, but I will add on. Again, try to establish the standard control limits if it is possible, because we can go on first, second, third, and beyond third we stop it. Why? Because we try to correct that one, and again fresh samples need to be, whatever the assignable reasons we need to find out and eliminate that one, and again run it and then collect the sample. Now the third chance we are giving, because anything, even if you look at most of these things, we will consider even in your internal tests, we are taking 3 tests. Okay, that is why usually first, second, third. Beyond third we don't go, because it will become repetitive. Let us see now. Now what has happened? 34 points and 13 lots we had considered. Now, the 10th sample, it goes out of control limit. So, we are eliminating that one. So, 34 minus 8, it is going to be 26. So, I am trying to calculate the revised P bar. 34 minus 8, 26. And how many lots now? Earlier there were 13, now one less, that is 12. So 26 divided by 12. So let us see how much it gives. So this is 12 into 400. This is 26 divided by 4800. So this gives 5.42 to the 10 to the power minus 3, or this is 0.0054. In 54, this is the average fraction defective. Earlier it was 0.00654. Now it is 0.0054. So we'll try to find out for this one, and then we'll stop discussing about this particular problem. Okay. So I'll find out again the revised this one. Now NP bar is equal to 400 into 0.0054 or 542. This works out to be 2.16. Okay. This works out to be NP bar, it works out to be 2.16. Earlier, it was 2.616. Now I'll find out NP bar, Q bar, square root of this one and multiplied by 3. That is what I need to find out. So NP bar is 2.16. Okay. Q bar 1 minus 0.0054. So let me consider it to be around 0.995, or to be precise, okay, we'll take 995, that is what I said, 0.995, that is what we can take it, Q bar. This works out to be almost 2.15, and if I take the square root, it works out to be 1.4682. Square root, this is 2 into 1.4682 and multiplied by 3. This works out to be, total value works out to be 4.4. 3 NPQ, this works out to be 4.4. Earlier it was 4.8, now it works out to be 4.404. Is understood? That means this one is 2.16. Now I'll write down clearly over here. Upper control limit. This is equal to 2.16 plus 4.04. NP bar is so much, that is the central line. Lower control limit, this is 2.16 minus 4.04. So this one negative, so it will become 0. This one is 2 plus 4, this is 6. 6.2. That means we will consider 6. Maximum number of allowable defectives are going to be 6, not more than 6. So central line is, instead of 2.216, we will consider it to be 2, and this is considered to be 6, and this is going to be 0. That means again the remaining 12, if we, after eliminating the 3 points, namely the sample number 4, sample number 9 and sample number 10, we are left with 12, not 15 lots, 12 lots, and their values need to be compared with the revised trial control limits. Revised trial control limits are, upper control limit is 6, central line is 2, lower control limit is 0. So we will try to compare these things. Okay. Now we can see that first sample is 2, second sample is 5, third sample contains 0, fourth we have eliminated, fifth sample it has 3 defectives, sixth has 0, 7 has 1, 8 has 0, ninth it was consisting of 18 which was removed, 10 it was consisting of 8 which was also removed, the 11 it consists of 6 defectives, 12 0, 13 3, 14 0, 15 6. That means all the 12 points have fallen on or within the control limits. Hence, this revised control limit is going to be the standard control, revised trial control limit. This I can standardize it for this particular process. So now it is standardized in the sense the maximum number of defectives allowed are 6. It should not cross more than 6. And of course, lower it has to be 0 only, it cannot go down below that. Okay. And the P bar, calculated P bar is 0.00542, because you could have used the P bar also, fraction this thing, that we would have asked. Okay. So here, that is how it is going to be implemented. So these things are fixed and they will go on taking the samples like this. Then plotting on the graph, it reveals what is happening. So actually what is expected is, it should hover around this central line, that is 2. It may be sometimes 2, sometimes 3, sometimes 4, sometimes 0, sometimes 1, like that. It should not fall on one side only. That is what we had discussed in case of the control chart for variable. The same thing is true here. Okay. So almost they should fall below the central line, which is expected, that is improving, that is good. If we find that it is on upper side, then it must have been the shifted, that is what it means, average value. If it is lower, yes, it is shifted, but it is shifted towards better. Okay. Now instead of 2, it might have shifted it to 1 defect. Okay, it is better, still better. Okay, but still, investigations are to be made. Why it is shifting like that? What could be the reason? So that it can be improved further. Okay, this problem gives the crux of these control charts for the attribute. This is one, that is what I had considered. Okay. Now we will see, because so far we were discussing about what? Almost NP chart. Because even though I considered P chart, but there also, since the variation from sample to sample was not much, we had considered the average sample size. Okay? And we could establish only for entire samples or the control charts, only two limits like this, entire thing. But actually, I had told you for P chart, it goes on varying. If the sample size varies, it will go on varying, whereas the central line will remain fixed. So let me take a small example and then try to see, because instead of taking some 10 or 15 samples like that, some 3-4 samples only will take and try to see how it works out to be, because we are just interested in knowing that. Okay? One minute, I'll just look for another example. Okay, some relevant example I could find. A P chart is used to analyze monthly record of or monthly record for 100% inspection of a certain radio transmitting tubes. Full point. The total number of inspected in the month are 2,196. Total number of the items, that means the radio tubes, inspected transmitting tubes, were 2,196 in a particular month. And the total number of defectives were 158. Total number inspected. Okay. Compute P and also the individual 3 limits for the production figure of the following 3 days, because 3 days and state whether the fraction defective fell within the control limit each day. So, he has made it a bit lengthy. Now, what he says is, these are the things given. Okay. Now, he says, we need to establish the control limits. Okay. What he has given us is only this much of information, and in the form of table, for 3 days, he has given the relevant information. What are those relevant information? Let us see. Day 1, days, numbers inspected, defectives, fraction defective, numbers inspected, that is what we will see. Because the first is, I will just write it so that you can, day 1, how many pieces were inspected? 54. Out of 54, 8 were defectives. On day 2, 162 were inspected and 24 they found out to be defective. And day 3, 213 were inspected, 39 were found to be defective. Okay? This is what has happened. So, what he says is, we need to find out whether the process was under control or not on day 1, day 2, day 3. Okay? Now, obviously, which chart is to be used? Because he talks about P, he talks about defectives. That means either P or NP chart is to be used. And if I look at the sample are varying to the great extent. It is varying from 54 samples to 213 samples. So just like that, I cannot go for average sample and do it. No. So individually it has to be done. So he has mentioned about that one. Let us not bother. Let us try to analyze the problem on its own merit and see what is happening. So P chart is to be used. Why? The sample size, it varies from one sample to another sample. Okay? Now, the control limits, upper control limits for P chart, we know that this is going to be P bar plus 3 under root P bar Q bar divided by N. Central line P bar. Lower control limit P bar minus 3 under root P bar Q bar by N. Try to observe here, P bar, Q bar, they remain same in all these things, 3. But only N, it goes on varying. For first day, the N is going to be 54. For second day, it is going to be 162. For third day, it is going to be 213. So this part, it will go on varying for each of these samples. But P bar, this central line or the average value, it remains same. Okay, that one thing I can find out right now what here is, if I consider this, first sample, second sample, and then the third sample. This is the P bar. Okay? Or the, not P bar, actually it is fraction defective P. So central line will be at P bar. What is the P bar? P bar he has given here. We cannot take up this one and then 8 plus 24 plus 39 divided by 54 plus 162 plus 213. No, not this one. In the absence of this data, I would have considered that. But only 3 samples are given. That means he has almost given the universal this thing data. That means totally he has inspected. How many of these things totally he has